Hey, everybody, and welcome to Double E's Talk Tech episode number, I think this is episode number 24.
Wow.
I'm Daniel Bogdanoff.
Mike Hoffman.
And we are back with Perry. And Perry, what are we going to talk about today?
We should talk today about getting your game on.
Getting your
for
game
next
on.
generation memory.
All right. Sounds exciting. So tell us about that.
Okay. Well, in the last 15 years or so that I've been focusing on memory, things have changed a lot from 133 megatransfers for pre-DDR to now to 6.4 and even faster for LPDDR5.
Gigatransfers. Right?
Gigatransfers, 6.4. 6.4 transfers per second. You know, the old slow is good.
With a billion bits at a time.
That's right.
There's pigeons inside the computer flying back and forth.
That's
with bits, yeah.
It makes things easier.
6.4
Anyway,
pigeons.
so but there's a lot of things that have to happen to, you know, if you're going to jack the speed up by a factor of 40.
Yeah.
And you reach certain critical thresholds that are driven by the laws of physics and material science and all that kind of stuff. And actually some of the things that this has been true for a long time. Some of the things I remember talking about 5 years ago about the memory wall are just as true today as they were then. But the one of the big deals I think that has changed is that memory being the kind of the last bastion of, you know, the old school single-ended wide clocked parallel bus has remained one of the most troublesome interfaces in any system design, and it's been very slow. It's been very conservative in how it adopts new technology. So when the buses, say when you got to DDR3 at 1600, if you looked at the actual timing budget for that, it was starting to close.
Okay.
And
we're well beyond that now.
Right. And so in order to step beyond that, a whole new set of concepts had to be embraced. And that resulted in DDR4. Now with DDR5, a whole nother new set of concepts need to be embraced. And that, when I say get your game on, it means you got to be ready to take on these new concepts and really understand them.
Now, is this basically what your paper was about at DesignCon most recently?
Yes.
Okay. Do you mind telling the audience a little bit about what DesignCon is, why you were there, kind of who attends?
DesignCon's held every year in January, and it's basically a big trade show for board designers and chip designers, you know, general electrical engineers, electronic engineers. There's a big exhibit floor with a bunch of companies there, and then there's a lot of different technical tracks. So it's not as sort of stuffy as, say, you know, an IEEE conference.
It's the trade show. For
The
that,
trade
I understand. So they, you know, I think Intel normally sponsors it, and
ChipHead's usually there. Did you meet ChipHead this year?
No, I didn't.
The one and only time I've ever gone is when we were launching the 4000X series. It was like 6 months after I started here. I didn't really know what I was doing, but I got a picture on the DesignCon homepage hanging out with ChipHead. He had my 49er hat on, and we were hanging out on the floor. It was pretty cool. I felt famous for a brief moment.
Did they have a good concert this year? I think we've...
You know, I actually missed that.
Okay.
I think I was busy skiing or something.
Okay. Because they had like Weezer, and I think Rick Eads, who did the PCIe podcast, was talking about like standing next to the lead guitarist from Journey as he was like jamming.
Oh, really?
Stuff
Wow.
like that, yeah. At DesignCon.
Station.
So, yeah. So if you go, it's, you know, the concert's a nice little side benefit.
Mm-hmm.
Oh.
Anyway, I'm sorry.
Yeah.
Cool. So you
Yeah.
presented all about the next steps of what designers need to prepare for DDR5. Is that correct?
Right, and DDR4, because that's really where the big shift in paradigm occurred.
So where are we now? And you talk about a paradigm shift. Are we kind of past that, or are we still learning from that shift? Or
It's being digested continuously.
Okay.
It's like swallowing an elephant, right? You got to do it a piece at a time.
bite at a time. Okay.
Right.
So what is being digested?
Well, if you look at the big picture, you can go all the way back, say, to DDR, and it introduced source synchronous clocking.
Okay. So
which-
DDR is double data rate.
double data rate, and the clocking scheme it wasn't with all the previous memories, it was basically a system clock, and that would govern when data was transmitted from the controller and received on the DRAM. DDR, the problem with that was transmission lines the timing out of skew, and so they went to source synchronous clocking. But you've got this whole realm here of what's called high-speed digital. You worry about transmission line delays. That's high-speed digital design.
Okay. What is source synchronous clocking?
Source synchronous clocking means that whoever's driving the data is also driving the clock.
Okay.
And so that's where this idea of a data strobe and read timing and write timing for being different for memory, which is a whole topic. But basically, it revolved around that transition into DDR strategies, source synchronous clocking, setup and hold times, trying to eliminate the effect of flight time on the transmission lines. Classic high-speed digital design.
Okay.
At 1600, that started to fall apart. And so for DDR4, the industry decided we got to go to a new mechanism.
So 1600 is 1600 mega
Right.
transfers per second?
Yes.
Megahertz? Okay.
What's a megaflop, by the way? So that was one of the cooler units in electrical engineering.
Megaflop.
Yeah.
It's when you trip with an
Floating
armful
point
of test equipment.
operations per second.
Okay. Is that
Million.
related to a transfer at all?
Not necessarily.
Okay.
Flop,
It's
it's like a processing unit, right?
Oh, okay. Yeah,
like-
I'm out in left field then. Never
a
mind.
megaflop is like a million floating point divides in a second.
Got it.
Oh.
All right, never mind. I'm sorry.
Like I think the first DEC VAX was cool because it was the first thing to do a megaflop.
Oh, okay. Sorry, we totally derailed you. So you're talking about the transition to DDR4 after
Yeah.
DDR3 1600.
So if you go from the high-speed digital concepts where things like timing diagrams, setup and hold times, propagation delays, noise margin, VIH, VIL, that kind of stuff. To go faster than that, you need to start thinking differently. You need to start thinking more like high-speed serial interfaces, like USB 3 or PCI Express Gen 2. And if you look in those standards, you don't see anything like setup time or hold time or any kind of stuff show up. It's things like noise and jitter and random and deterministic and bit error rates and Q factors and all that kind of stuff. Well, the reason for that is because you can't control the precise timing as cleanly, and the each end of the system needs to be able to adjust itself. But the thing you count on is where the data I is, right? So you got it moves around, and you got to be able to follow that. And as long as the receiver can follow where that data I is, you can capture the data reliably. Completely different concept.
Yeah, totally.
This is using an embedded clock. Is that correct?
No. Well, and that's the thing about DRAM still is it doesn't use an embedded clock, and the reason for that is latency. Again, latency and power is king here. There's a lot of overhead in embedding the clock, and that reduces channel efficiency, which when you're looking at sort of the very deepest core information transfer between the CPU and memory, you can't tolerate much inefficiency there.
Okay.
DDR is it single-ended line, correct?
Yes, for data, it is, but more over time, more of the control signals like the strobe have become differential, but the core of it is still single-ended.
Okay. So is it safe to say that a lot of high-speed digital processes and techniques are coming into DDR? Is that?
Yes,
Okay.
but there's you can't just drop them in. So if you look at the transition from the DDR 1, 2, 3 to DDR4, you're making this transition from high-speed digital thinking to high-speed serial thinking, which is basically means data I is random deterministic.
Okay.
The thing that you run into with DDR5 is that the I is closed. So just as people start to swallow the idea of, okay, we've got to manage this data I and random jitter and all that stuff, DDR5, it immediately hit this, what I call the impulse response threshold, where there actually may not be an OpenEye anywhere that you can see, and you need to have an equalizer in the receiver.
Huh, that sounds horrible.
Well,
for designers.
It's a paradigm shift,
Yeah.
and that's the thing is, you do something for 20 years, you master that, and then you need to move to a different way of thinking about how do you do your design, how do you write the specification, how do you test it.
It's a good lesson for everybody.
Yeah. So when I say get your game on,
Get everything you know. Yeah.
it means it's like you're going to go from snow plowing to parallel, right? Or
Sure.
you're going to start mastering the bumps or something. You got to think about what you do differently.
Okay. Good skiing reference there if anyone missed that.
Yeah.
Those weren't weird memory terms. That's what happens when you live in Breckenridge. So you talked about, DDR is basically the last more or less the last remaining parallel communication system.
Traditional.
What is
parallel.
it communicating to? So it spits out a bunch of data. You have a DIMM on a board.
You have a controller on one end, which is the usually the CPU.
Okay.
And
So the
then the
CPU
other
just
side is
has a bunch
the
of
memory
pins.
devices.
Okay.
Right.
So and then what you're saying then is that a lot of with DDR5, the eyes closed, the receiving end of all that is going to have to start implementing a lot more also. So it's
Yes.
twofold.
Yeah, but I think the big deal with that is understanding the concepts of equalizing receivers and how do you train, how do the controller and the memory work together to keep track, to open the eye back up and then keep track of it as it moves around as like temperature and voltage shifts and being single-ended, there's a ton of crosstalk on the bus. Those are the things that make memory different than high-speed serial. Those
Okay.
are all differential.
Okay. Are there engineers who have pretty much spent a lot of their career working on DDR and they're now like branching out into this, or do people tend to kind of bounce around between the two types of technology?
They've generally been different groups.
Okay.
I think what I've found is that the memory guys, are pretty much, they're black hats in that area, and the I/O, which is where the high-speed serial stuff came from or started with InfiniBand. They've been responsible for different parts of the system, and that's been because the concepts are different.
Mm-hmm.
But now everybody's being dragged kicking and screaming together.
Okay, that makes sense.
And the next step with DDR5 is maybe one of the last steps before people have to start grappling with data communications theory and complex modulation or something like that. If 3D silicon doesn't save the world, somehow more bits got to get pumped through the same copper.
It blows my mind that DDR, for being how high speed it is still single-ended. Yeah.
Yeah.
I just imagine it's like you were asking, kind of how does it work? What are we communicating parallel to? The way I always imagine memory, and correct me here because I'm sure I'm wrong, it's like a big grid basically, and we're coming in with say 16 lanes wide, and then it's just kind of going as deep as it needs to find 16 bits to pull back out of like a register. Is that kind of what's happening in some way, shape, or form, or is it like a big bucket of memory?
You could think of it like best analogy is like you allocate an array, in C or something like that,
Yeah.
and you got it's just a big pile of bytes, right? And at its core, that's the programming model. But then in a system, that 8 bits is a very narrow pipe. So most PCs you see now will have, say, two channels of memory running in parallel. That's 128 bits, so that's 16 bytes at once. Graphics will run even wider, 500,000 bits wide, and often they are decoupled, so that the channels are independent. You might have one GPU talking to this channel of memory, another GPU talking to another. But at its core, the concept is basically got a big array of bytes that you're accessing.
So what is I'm not familiar with 3D silicon. What's the allure of that?
So
and what happens if that doesn't come through?
Well, then people are going to have to push more bits through copper.
Okay.
So the promise of 3D silicon systems is that you're not limited by how many solder bumps you can put onto a package. You can use the solder bumps that go on chips. Between them are much smaller. You can pack them much more tightly. So you could conceive of, say, interfaces that are 10,000 bits wide or long or more.
Jeez.
And if you go wider, you don't necessarily have to go as fast to get the same throughput.
How do you get that off the chip?
You solder the two chips together.
Okay.
You bond them together, and that's why it's 3D. So you take like a CPU chip, and on the top of it, it's got pads, and on the and you put on top of it, say, a memory chip.
Okay.
And they basically are soldered together. The trick is that if you want to get more memory, then you got to stack more chips up on top.
Right.
Which means you got to have vias that go through. That's where the silicon through vias come in.
Which becomes basically the same challenge, right? Is at some point, if you have a 2-inch stack of memory and a 2-inch trace on a board.
There's that, and but the big thing that has delayed 3D silicon adoption has been that it turns on its head the entire design, the entire value delivery system. How you do the design, how you do the testing, how do you do failure analysis, who owns the IP for doing manufacturing testing, because you got different companies, contributing to this one thing that's got to all be tested together, and you can't break them apart. Back it was about 7 years ago when JEDEC first started working on wide I/O.
Okay.
There were like 500 reasons I could list why it wouldn't work. Now there's maybe 50.
Sure, we're getting there.
Yes, but it's going to take a few more years before, before I can, probably 10 years before I could go on the internet and say, okay, I want to, you can get PCBs made, right? Easy as a maker or something.
Right.
At some point, you may be able to do that with silicon, but it's going to be a while.
Huh.
Now, what's the difference between this 3D silicon technology, stacking memory on top of a processor or whatever, versus just having it all integrated into a processor? I know I just heard some chip manufacturer earlier this week just came out with some really trick CPU GPU combo that has all the GPU memory on board, and it benchmarks better than, of course, any integrated chip did before, and even better than a lot of entry-level standalone graphics cards. What's the advantage of the modular technologies, and why would big manufacturers buy into that versus just building it all into their own black box?
Well, it's generally the difference between working in 2 dimensions and 3 dimensions, and so the available semiconductor processes right now, except in special cases, still work in 2 dimensions. So you want to add a CPU and cache or something, you can't put it on top of each other. You got to make the chip bigger. If you go 3D, then you can keep things smaller, and instead of making, say, 4 connections, you can put in 8.
Well, I know like silicon, or the boards at least, tend to be layered. So are you telling me like a lot of chips today and processors today aren't layered, or are we talking about a different type of
layers?
3D?
Layers on a chip are more about like the architecture of individual components.
It's for pure interconnect.
Right.
But the active devices basically are spread out over a 2-dimensional floor plan. Now, for flash memories, the big deal has been improving on that so that they can actually build layers on top of active layers for flash. But there's some special economics there that make that attractive. For general circuits, digital systems, you've got to stack. You got to do each piece on separate die, and you connect them either through a silicon interposer, which is still a 2D layout, or if you can stack them one on top of the other, then that big wide area gets compressed to a smaller volume.
You can't really, like on a chip, you can't grow more silicon on top and start redoing stuff necessarily.
You can, but it's a technology that's in its infancy.
Right. So for now, it's pretty much you start with a wafer and you dig into it and then throw some metal on top. And that's kind of
Yeah,
very
that's-
crude. You know, I'm sure
That's
there's
kind of
comments will
how
go
I
wild
do
on
it
that,
at home.
but
Yeah.
Yeah, that's what you do at home too. Yeah. All right.
Well, I'm sure the ability to stack like that's going to be huge for mobile because right now I know the struggle is to try to compress the silicon space to improve more, have more space for a battery. Is that kind of one of the use models for that?
Wide I/O. That was the vision behind the Wide I/O 1. Was that you could, if you could do that, you could reduce power because you could go very wide, and you could get really insane throughput at a relatively low interface speed in a very tiny package, something that wasn't bigger than what you have now. So that was the idea. That was the vision, and I mean it's still good. It was just those 500 technical and legal reasons and practical reasons that stood in the way.
Okay, so we're running up on our time again. Are there any closing, wrapping back to our original topic? Anything you want to hit there?
Yeah. Well, I think the main point really is that if you're looking at, when do I go from, say, DDR1, DDR2, DDR3, it's really kind of just jacking up the clock rate, but the basic design principles are the same. If you're going to go faster with things like DDR4, you've got to become comfortable with high-speed serial design concepts, statistical, random, deterministic quantities. What an eye diagram is instead of setup and hold times.
Okay.
And then if you want to go beyond that, when DDR5 is ready, you're going to have to throw away the concept of an open eye and move towards the impulse response of equalizing receivers.
Okay. Are there? I just totally lost my question.
Was that the gist of your message at DesignCon for the audience there?
Yeah, it was basically if you're going to bite this off, get your game on.
Okay.
Because you're going to have to learn and do things differently.
I remember my question. As much as you can say publicly, where is technology today with DDR? What's been...
Well, DDR4 has become mainstream. It takes about 4 years or so to develop a new generation.
Okay.
So, work started in JEDEC on DDR5 about a year or so ago.
Okay.
And then work sort of homework even precedes that. So we're still a ways from having it released and shipped.
Okay. Are you? I know we do a lot of non-disclosure agreements. Is there silicon out there for DDR5? Is that being?
I could tell you,
prototyped?
but then I'd have to kill myself.
Okay, fair enough.
Not me though. Not us. You want us to carry the message forth?
Well, we're fine. You and I, we don't know the guy who's going to come for.
I mean, if I
Barry,
could kill you, I would do that. But killing me, I care more about.
Fair enough. Okay. Stupid questions, Mike? Any?
Yeah. What was your? Do you have a favorite booth at DesignCon this year? Did you get to go explore around, and why? Like free swag or food?
Other than the Keysight booth, because that's the answer you have to give. Right?
Yeah, I guess my favorite booth was the one with the munchies on it.
Continue. What do you mean?
Go on.
Well, they serve. Sometimes they bring food out, right?
Yeah.
Okay.
I mean, if you want to get a bunch of engineers together, all you have to do is bring food.
Yeah. I know. We should put a couple kegerators in the Keysight booth, and we'd be good to go.
Dude, we do that out
That's
at
right.
Embedded World. Well, you were there last year as a cutout, so that was pretty
As
close.
a cutout, I was. There was a cardboard cutout of me there.
I mean,
pretty good.
can I get a stand-up made?
Yeah, that's what we had. Yeah. Anyway, I think we're out of time. I don't have a question. I didn't think ahead here enough. So
I have no useful answers anymore.
fair enough. Thank you for watching. Make sure you subscribe to Double E's Talk Tech in your favorite podcast engine. You can also go to doubleestalktech.com, put in your email address, get an update as soon as we post a new episode. And of course, follow us and subscribe to the Keysight Labs YouTube channel and the Keysight Podcast YouTube channel. Yeah, go ahead.
You know what? I just realized something. I've been subscribing to our podcast on my least favorite podcast engine. I'm doing it all wrong.
Why?
Aren't I?
Oh, man. Yeah, you really are.
Okay.
I also realized I should be wearing purple right now. Mike is wearing the same purple shirt in every episode, just for the record.
So I picked.
Doesn't
right.
smell bad yet, does it?
I haven't noticed.
Okay, good.
Anyway, we should probably be done. So thank you for watching. We will see you next time. Cool.
You're about 20
Awesome.
minutes and 40 seconds.
Okay.